This is the surface of one of the most mysterious worlds in our solar system. For thousands of years, we watched this planet without ever really understanding it. We named it Venus. For most of human history, we believed it was our twin. But there was just one problem. No one had ever actually looked. In 1962, NASA's Mariner 2 became the first spacecraft to conduct a successful flyby of another planet. It swept past Venus at a distance of roughly 34,800 kilometers. The instruments did not detect a swamp. They detected a furnace. The surface temperature came back at approximately 425 degrees Celsius, hot enough to melt lead. The atmosphere, far from being a shield, was acting like a lid. A planetary pressure cooker trapping solar heat in a feedback loop with no exit. This was the first measurement of a runaway greenhouse effect on another world. The model was wrong. Completely, catastrophically wrong. And it had taken one flyby to destroy what centuries of astronomy had assumed. But that was just the beginning, because what scientists have discovered about Venus in the decades since has not clarified the picture. It made it stranger. For most of the late 20th century, Venus was treated as a geologically dead world. Yes, it was hot. Yes, it was covered in volcanic rock. But the accepted model held that whatever made Venus volcanic happened a very long time ago, roughly 500 million years back, during a catastrophic resurfacing event that cooked the entire surface and then shut down. After that, the planet was assumed to be geologically static, frozen in place, a fossil. This model persisted largely because it was never seriously tested. NASA's Magellan orbiter arrived at Venus in 1990 and spent 2 years mapping 98% of the planet's surface using synthetic aperture radar. This was a system that fired radio waves through the clouds, bounced them off the surface, and reconstructed the terrain from the reflected signal. The resulting maps were the most detailed images of Venus ever. They revealed massive shield volcanoes, plains of hardened lava, and rifting terrain that looked geologically active. But Magellan's mission was to map, not to monitor. It took snapshots, not movies. No one thought to compare those snapshots closely, not for 3 decades. In 2022, Robert Herrick, a planetary scientist at the University of Alaska Fairbanks, had an idea. He was part of the science team preparing for NASA's upcoming Veritas Venus mission. To test what the mission might find, he started manually examining archival Magellan radar images taken months apart over the same region. He was looking for change. He spent over 200 hours on the work. He didn't expect to find much. Then he saw it. A volcanic vent on the flanks of Venu's tallest volcano, Maat Mons, rising 8 kilometers above the surrounding plains, had changed. In February 1991, the vent appeared nearly circular, covering an area of roughly 2.2 square kilometers. It had steep walls and clear signs of drained lava down its outer slopes. 8 months later, in October 1991, the same vent had doubled in size and become misshapen, like a kidney bean. The interior appeared to have filled to the rim, consistent with a lava lake forming during an active eruption. Adjacent terrain had brightened, suggesting fresh lava had flowed downhill. This was not a feature from 500 million years ago. This happened while the spacecraft was in orbit. The implication was significant. If Magellan could catch an eruption by accident in only 24 months of surface imaging, then eruptions on Venus are probably not rare at all. Herrick estimated that Venus could be experiencing eruptions every few months, a rate comparable to Earth's most active volcanic systems. A 2024 follow-up study by researchers in Italy, published in Nature Astronomy, independently found evidence of 2 more eruptions from the same archival dataset, one at the volcano Maat Mons and another in a region called Niobe Planitia. The Maat Mons flow alone produced roughly 30 square kilometers of new rock, enough material to fill 36,000 Olympic swimming pools. Venus is not dead. It never was. And a planet that is actively reshaping its own surface is a planet doing something. When you look at Venus in visible light, the planet appears almost featureless, a uniform white sphere wrapped in an unbroken shroud of sulfuric acid clouds. But when you look at Venus in ultraviolet light, the picture changes entirely. Dark streaks and patches appear across the cloud surface, swirling and shifting with the rotation of the upper atmosphere. These features move at roughly 360 kilometers per hour, faster than any storm system on Earth's surface, cycling around the entire planet in just 4 days. The dark patches absorb something. The question is, what? Astronomers first noticed this ultraviolet contrast as far back as 1928, when F.E. Ross published photographs of Venus showing unusual high-contrast features in the UV spectrum. Nearly a century later, the identity of what is causing this absorption remains unresolved. The scientific community refers to it simply as the unknown UV absorber. What is known is that this absorber is extraordinarily effective. It captures more than 50% of all solar energy reaching Venus. That is not a minor chemical curiosity. That is a dominant force controlling the planet's energy budget. Whatever this substance is, it is doing more thermodynamic work on the atmosphere of Venus than anything else scientists can currently identify. Without understanding it, the models of Venus's atmosphere, its temperatures, its circulation, and its chemistry cannot be completed. Researchers have proposed dozens of candidates over the decades: sulfur compounds, iron-bearing minerals, organic molecules drifting in from interplanetary dust. A 2024 study from the University of Cambridge synthesized iron-bearing sulfate minerals in conditions designed to mimic the Venusian cloud environment. They found that 2 specific minerals, rhomboclase and acid ferric sulfate, produced UV absorption patterns broadly consistent with what the Pioneer Venus spacecraft measured in the 1970s. The chemistry, they concluded, was at least plausible. But there was a catch. These explanations assume the chemistry of Venus is in equilibrium. The ingredients reacting in those clouds have reached a stable, predictable balance over millions of years, and that assumption has its own serious problem. A planetary atmosphere in equilibrium behaves like a well-run chemical factory. Inputs come in, reactions occur, outputs leave, and the whole system finds a steady state. Earth's atmosphere is not in equilibrium. It has oxygen, which is chemically reactive and would disappear in a geologically short time if life were not continuously replenishing it. That disequilibrium is one reason scientists searching for life on exoplanets look for atmospheric oxygen as a potential biosignature. Venus's atmosphere should be in equilibrium. The planet is covered in volcanic rock and bathed in sulfuric acid clouds. The chemistry should be settled, predictable, dominated by slow and well-understood reactions. It isn't. The list of unexplained observations in Venus's atmosphere has grown steadily over the past several decades. Sulfur dioxide, which should be produced by volcanic outgassing and accumulate in the upper atmosphere, is instead depleted precisely in the cloud layers where it should be most abundant, and the mechanism removing it is unknown. Water vapor behaves erratically, appearing in concentrations that atmospheric models cannot reproduce. The cloud decks between 48 and 70 kilometers altitude contain particles whose composition has never been definitively identified. And below those clouds, in a hazy, stagnant layer between 31 and 47 kilometers altitude, researchers have detected trace amounts of gases that simply should not exist there, including oxygen, hydrogen sulfide, and methane, all in combinations that reaction chemistry says should neutralize each other almost immediately. Something is producing these gases continuously. If it were a volcano, scientists would expect the amounts to fluctuate with eruption cycles. They don't clearly match. If it were a purely chemical process, theorists would have modeled it by now. They haven't. Then, in 2020, a team led by astronomer Jane Greaves at Cardiff University reported something that stopped the planetary science community cold. Using the James Clerk Maxwell telescope in Hawaii, they detected a spectral signature in Venus's cloud layers consistent with phosphine, a molecule made of phosphorus and 3 hydrogen atoms. On Earth, phosphine is produced almost exclusively by living organisms and by industrial chemical processes. Does not occur naturally in oxygen-rich environments. Finding it in the clouds of Venus was, as one researcher described it at the time, something that by all normal expectations should not be there. The discovery was explosive, and then it started to collapse. Follow-up analyses found that the original data had been miscalibrated. The signal was roughly 20 times weaker than the initial measurement suggested. Several independent observatories could not reproduce the detection at all. A 2023 attempt by NASA's Sophia Airborne Observatory found no phosphine in the upper atmosphere where it had reportedly been seen. The Nature Astronomy paper still carries an editor's note advising caution. But Greaves and her team did not give up. By 2024, they had gathered new observations from a third telescope instrument. Now, much weaker, but still present, that signal was appearing again. Not at the level of the original claim, but not zero either. The scientific community's verdict remains split. The phosphine may be real and produced by some unknown geological process. It may be a detection artifact, or it may be something else entirely. What no one has yet been able to do is definitively explain where it is coming from, or definitively prove it isn't there. There is a region in Venus's atmosphere that, on paper, does not seem particularly hostile. It sits between 48 and 60 kilometers above the surface, high enough to escape the crushing heat below, but low enough to remain sheltered from the lethal radiation above. The atmospheric pressure at this altitude is roughly 1 atmosphere. The temperature is between 0 and 60 degrees Celsius. For context, that is colder than a summer day in Phoenix, but warmer than a winter morning in Moscow. The pressure is nearly identical to standing at sea level on Earth. If you could somehow remove the sulfuric acid, it would almost be temperate. This is where the atmospheric anomalies are concentrated. This is where the unidentified UV absorber is most active. This is where the sulfur dioxide is being depleted by an unknown mechanism. This is the altitude range in which phosphine would most likely be present, if it was even real. This is also where researchers in 2023 from MIT reported detecting the presence of what appear to be non-spherical cloud particles. Round droplets are liquid. Non-spherical particles are solid. Something solid is forming in the clouds of Venus, and its chemical identity has not been established. Separately, a 2023 paper published in the Proceedings of the National Academy of Sciences by Sarah Seager's group at MIT reported something even more unusual. The researchers were testing whether the building blocks of biology could survive in concentrated sulfuric acid, which had generally been assumed to be incompatible with organic chemistry. They found that nucleic acid bases, the molecular components of DNA and RNA, were stable in the acid concentrations found in Venus's cloud droplets, not destroyed, not degraded, chemically intact. This does not mean life exists in the clouds of Venus. What it means is that the previous assumption that sulfuric acid clouds make life impossible at that altitude was not tested. It was assumed, and the assumption was wrong. Whether the anomalies in that cloud layer have a biological explanation is a question that cannot currently be answered. The instruments needed to answer it have not yet been sent to Venus. For a long time, the prevailing theory held that Venus was once habitable. NASA's Goddard Institute for Space Studies ran climate models suggesting the planet may have maintained stable temperatures and liquid water on its surface for billions of years, potentially as recently as 715 million years ago. Given that life on Earth took hold within a few 100 million years of the planet's formation, a billion-year window of habitability on Venus would have been more than long enough. Then, in 2024, a team at the University of Cambridge upended that model. Their research, led by Teresa Constantinou, examined the geochemical signatures of Venus's volcanic history. The finding was blunt. Venus's volcanic eruptions appear to have been dry, unlike Earth's volcanoes, which release significant quantities of water vapor. The evidence suggests the interior of Venus has never contained substantial water. If the planet's rocks were dry from the beginning, there was likely never a sustained water cycle. There were likely never oceans. And without oceans, the conditions for complex chemistry that preceded life on Earth may never have existed. This contradicts the optimistic models. It also contradicts the atmospheric measurements that suggest Venus once lost significant water to space. The Pioneer Venus probes detected an abnormally high ratio of deuterium, heavy hydrogen, to ordinary hydrogen in the atmosphere. On Earth, that ratio is a marker for ancient water loss. If Venus had the same enrichment, the standard interpretation has long been that water once evaporated from its surface and escaped into space over geological time. The Cambridge findings suggest the water was never there to begin with. Both interpretations cannot be entirely correct. The data points in opposite directions. And at the center of that contradiction sits a planet that is actively volcanic, chemically strange, and almost completely unvisited for the past 4 decades. The last spacecraft to successfully land on the surface of Venus was the Soviet Venera 14 probe in 1982. It survived for 57 minutes before the heat destroyed it. The images it transmitted showed a flat, basalt-covered plain under an amber sky. That is the most recent direct visual record of the Venusian surface that humanity possesses. It is over 40 years old. The most detailed radar maps of the planet come from NASA's Magellan mission, which ended in 1994. Magellan mapped Venus at a resolution of roughly 100 to 300 meters per pixel. For comparison, modern Earth observation satellites operate at resolutions below half a meter. Scientists studying Venus are working from maps that would look coarse on a roadside atlas. 3 new missions are currently in development. NASA's Da Vinci deep atmosphere Venus investigation of noble gases, chemistry, and imaging is designed to drop a probe directly through the Venusian atmosphere, sampling the chemistry layer by layer as it descends towards the surface. It is projected to launch in the early 2030s. NASA's Veritas mission, which originally inspired the discovery of the Maat Mons eruption, was designed to produce high-resolution 3D radar maps of the planet's surface. It has faced repeated funding delays, with its launch timeline now pushed well past its original window. The European Space Agency's Envision mission, meanwhile, is planned as an orbiter that would study Venus's surface, atmosphere, and interior using radar and spectrometers. None of these missions has launched. None will arrive before the early 2030s at the earliest. In the meantime, the questions multiply. Venus is the brightest object in Earth's night sky after the Moon. Ancient civilizations tracked it, named it, built temples aligned to it. For thousands of years, human beings watched that brilliant white point rise and set, and told stories about what it was. None of those stories included a planet with 90 times Earth's atmospheric pressure, temperatures hot enough to melt tin, sulfuric acid clouds, active volcanoes erupting new lava fields in the span of months, and an atmosphere that refuses to reach chemical equilibrium. This is the actual picture. It is a planet where the geology is still running, where the atmosphere carries gases that the chemistry says should not be there, where the clouds absorb more than half of all incoming solar energy through a mechanism that no one has yet fully identified, and where the one altitude range that could theoretically support some form of chemistry, or maybe something stranger. The standard scientific position is that Venus is a dead, hostile world with no relevance to the question of life in the solar system. That position is built on models derived almost entirely from data collected between 1962 and 1994. The instruments that gathered that data were not designed to look for biology. They were designed to measure pressure, temperature, and terrain. This question is not whether or not something strange is happening on Venus. The question is why, after everything those old Soviet probes sent back, the chemical anomalies, the UV absorber, the non-spherical particles, the atmospheric disequilibrium, the next generation of missions took 4 decades to be approved and longer still to fly. Until Da Vinci drops through that atmosphere and Veritas maps what is burning below, what Venus is actually doing remains one of the most unresolved questions in planetary science. The amber sky in the Venera panoramas, the volcanic plains reshaping themselves in 30-year-old radar images, the dark UV streaks rotating at 360 kilometers per hour across those cloud tops. All of it is still, somehow, mostly unread. We have a neighbor that is alive, curious and close. We just haven't looked closely enough.